Hi there, I'm Greg Watson. Today we're going to talk about planning the abandonment of Six Sigma, shifting the legacy. Now that sounds like a very controversial title, and it's meant to be. Because what I'm trying to do is to get us to stop and reflect on what Six Sigma is, how the model is working, how the tools are working, and to understand what do we need to do to make continual improvement of the process and the tools for the coming decades ahead, given the current state of change that's happening around digital technologies and the application of Six Sigma in a wide variety of areas, not just the original manufacturing applications that happened in the early 1990s, where it originated and the models were first developed. And so what I want to do is talk about some things. So we'll talk first of all about the need for a universal continual improvement model. Why do we believe that this is necessary? We'll then talk about the description of a continual improvement process model developed by the International Academy for Quality in a 3-year study by a think tank on designed improvement between 2014 and 2017. And then we'll talk about what are the quality methods that require revision or reinvention to be able to fit the coming digital age that we're moving into. Now, Quality 4.0, in my mind, is actually a disruptive event. And the question is, what will it disrupt? And we have to go back and take a look at that. Some of the things it will disrupt are the transitory state we're going from the old ways of doing quality to a new way that's yet to be defined. And part of examining our past and being critical about it, making critical judgments about what we know and what we don't know, and how to make it actually work in the context of an organization in a better way, those are the things that quality thought leaders need to do to bring us into that new age that's emerging out of the past. And so this is a call to action for the quality community. We have to think, what will we do? How will we take on our responsibility as quality professionals? That does not mean we sit back and just let it happen, or we keep repeating the past. We have to consciously take a look at quality as a science. Science is never settled. It's always open to improvement and development of new theories, testing those theories, and moving them forward as they prove themselves over time. And that's precisely what I am proposing in this lecture today. So what I want to do is get us to challenge. What are we doing with Six Sigma? Should we get rid of it totally? Is there a place for it in an organization? Do we need to continue with DMAIC, use it differently, or use models in a totally different way as a systems engineering approach to how we do continual improvement of organizations? Now, innovation means abandoning the past. The economist Joseph Schumpeter talked about this in his books in the 1960s or 1950s. And in 1952, he wrote a book called Capitalism, Socialism, and Democracy. And there he said, success depends on intuition, on seeing what proves afterwards true, but cannot be established at the moment. And so when we have something in science, we begin with a hypothesis, a research hypothesis, not a mathematical one, and it's basically a guess. And what we want to do is say, this looks interesting. Can we try it? And in this book, Capitalism, Socialism, and Democracy, he described how systematically destroying and replacing old ideas by new ideas, planned abandonment, getting rid of the old ways of working, what we call legacy systems. This is what he called creative destruction. And this is now accepted as the foundation principle in terms of innovation. In Europe, the European community has used this as the basis of the Lisbon Accord on innovation. And so we have to say, what should we get rid of in order to embrace the new and not burden ourselves with the legacy systems that no longer apply? And by continuing them, all we do is produce waste and confusion in our systems as we move forward. And so this is no longer our grandfather's quality. I look back and I see, Dr. Ishikawa never used a personal computer. Dr. Duran was not literate in terms of computer technologies. Deming used a typewriter. Duran said, I want to die with my hands on the keyboard of my word processor. And so you get the idea. These guys were not literate in terms of digital technologies. Armand Feigenbaum may have been an industrial engineer, but he also did not actually do things. He read his speeches from a notebook that were all typed out in terms of large font so he could read them. Now, one of my favorite Japanese haiku is by Matsubasho. And he said, "Do not seek to follow in the footsteps of the old masters." In other words, don't try to do exactly what they did. Don't necessarily apply the same tools they applied. Seek instead what those masters sought. In Japan, there's a way of stating this. They say, shu ha ri. So shu means to keep, and that's the first level of training. You can go and apply the kata, what has happened, but then you don't accept it. And so ha means to move away, and that means you take and you adapt those things to a new situation. And ri means to break, and that means that you find new ways to innovate what is you've learned based on what the masters taught. So quality, like science, is never a settled discipline. It must evolve and develop so it's appropriate for the current age and its technologies in a way that maintains its relevance. Now, there's a need for a universal continual improvement model. And this was the purpose of the ASQ think tank, which I was leading with my colleague from Sweden, Lars Sorquist. And what we saw was we had come at a request of the European Organization for Quality, and they asked us, please, can you help us standardize Six Sigma? And the reason in Europe this was necessary is that Europe did not grow up under the ASQ umbrella of Six Sigma. Many companies, because there was no European approach, either used the ASQ approach or developed their own. So large companies like Siemens, Philips, and so forth created their own approach to Six Sigma based on their past technologies and then bringing in what they thought was necessary. So what we see in Europe at that time, 2014, was chaos. And so every country was doing things differently based on how different consultants taught it. One group in Italy even started in 2007, and they said, come to us because we have the trademarks for Green Belt, Black Belt, Lean Six Sigma, and Master Black Belt, and DMAIC and DMADV. But of course, those were only trademarks in Italy, and they had nothing to do with any sort of intellectual property creation. It was all marketing. And so it had actually, this whole Six Sigma approach had been driven by consultants, mostly through a marketing approach to get sales and revenue. And so what we saw was, as we looked at this and compared all of these models, it wasn't just a standard that was necessary, but there was all sorts of confusion because Japan never accepted really Six Sigma. There are companies there who've done it. So we see that there are companies like Toshiba, who is using a Six Sigma DMAIC model. There's other companies like Shimano, the company that makes sporting goods, they've used the Six Sigma DMAIC model. Some of the other copier companies have also used it. However, in general, they use Japanese total quality management. So they use a totally different approach. And we see other communities around, like accountants, using activity-based costing as a modeling process. And we see the information technology people using their models for improvement. And so that might be business process reengineering or business process management. So if you take a look across the wide variety of different communities who are trying to drive continual improvement in each of those disciplines, we see it's all different. So from this, we got the idea there's a need for a universal continuum model. So we started this project based on this EOQ request that we proposed a standard. We established a think tank, and then we looked at the models that were proposed during the last century. We analyzed them and then integrated them into a composite continual improvement model that creates a generic approach that's applicable to all of those methods and is appropriate for all of those disciplines. Now, what I want to do is go through some of the models that we have seen in the past. The most famous model, perhaps, is the Shewhart cycle. And this Shewhart cycle documents the thinking of Taylorism. So Frederick Taylor created an approach which we would call Plan, Do, See. As a matter of fact, that is exactly what the model was called in the Efficiency Society in Japan in 1912 when they took on the translation of Frederick Taylor's work into Japan and they tried to reduce it. So what Taylor did in his model was he was adding the inspection function to the division of labor created by Adam Smith. So Adam Smith had the division of labor between management and workers, planners and doers. And so what we see in the Shewhart cycle was he actually in 1939, in his work Quality from a Statistical Point of View, talked about specification, production, and inspection, plan, do, see, or hypothesis, experiment, and test of hypothesis. And so this was the beginning, if you will, of a structured model for improvement that we saw. We call it the Shewhart cycle. Now, the Shewhart cycle treats workers as a pair of hands. It doesn't engage them in the planning or inspection functions, and the model results in work that's either mandated by the management function or it's a result of correcting complaints from the inspection function that's policing compliance with work procedures and results, which were also defined by management. Now, this cycle is most appropriate for describing either the statistical analysis process or an engineering design process, but it does not describe a total productive system. And that's the problem. It cannot be used as a generic model. We see then Japan came up in 1959. Shigeru Mizuno, who was leading the Japanese Union of Scientists and Engineers QC Research Committee, came up with PDCA. Now, the reason he came up with PDCA, Plan, Do, Check, Act, or Design, Experiment, Analyze, Feedback, as a control cycle was that the work that had been done up to that point in time did not comprehend the A part. And he wanted to merge together the thinking that Deming had in his lectures in the early 1950s with what had been happening with the Efficiency Society and the Plan, Do, See model. And this was referenced by Karuo Ishikawa in his 1989 book, TQM, The Japanese Way. Now, the problem with PDCA is that it actually has some concerns. Now, it exists in numerous forms. Every consultant, major consultant in Japan, had their own version of PDCA. Mostly it was called a control cycle. Some called it a wheel. Some called it a process. And so we started taking a look and we saw it was actually different. It didn't really create a standard at that time in the 1950s through the 1980s. So the model was applied for both control of the daily work processes and the improvement of that work. Now, the second level of this was actually never fixed by the research committee. They only came up with that top level, Plan, Do, Check, Act. So they didn't say what you did within those steps. And this is where there was a lot of diversity. So every company defined their own approach. And so we started seeing people applying that model in very different ways. And some were doing a very good job, and some actually not, because they weren't as sophisticated or mature in their thinking about how to address problems. And while Dr. Ishikawa had identified the 7 basic QC tools, they were not a part of the PDCA model. Not until 1987, when a model was created of PDCA applied by Hitoshi Kume in his book, Managing for Quality, was that in existence. And that was because he was the lead in terms of helping Florida Power and Light apply for the Deming medal. And that was the first non-Japanese company to receive the Deming medal. And they wanted to have the tools related to the process. So the front end of the process is not linked to strategy formulation. It's only basically plan. So the plan is about understanding what we're doing. And the back end doesn't result in standards. It results in the adjustment to the process. So as we start seeing, there's something missing. And because there was something missing, the Japanese actually added a precursor to that process called Standardized Do Check Act. Now, this grew up in the 1990s, and it grew up the same time Six Sigma was developing in the West. And it's actually documented in the Japanese Society for Quality Control standard on daily management, which exists in English. If you go to the JSQC website, you can download that standard. And so their idea of standard work is basically, this is the job of the worker. Do work and improve work, the Kaizen cycle. And it all is based on the standards. So you spend 80% of your time doing the work. That's the value-adding work. Every person is responsible for checking that work. And then if there's checking is not right, and they have the capability within their responsibility and the decision rights that have been delegated to them, and they can do it within their budget, then they can act, and then they can standardize based on the action, and then return back to the productive work. However, if they can't do it within their decision rights, if they can't do it within their budget, then it reverts back to a change management process. So the pivot point comes out of check and it goes to act at the supervisor level. And the supervisor has more freedom to act not just within a single production cell, but across the flow of the processes. And then they can plan how to deal with that and then go through to make the changes. And once that becomes stable, the check step reverts it back in and it's adjusted to the work cell, and it goes back to daily management. So this was a process model. It has not been actually very well documented in the West, but it is a part of Japanese TQM. Now, we have some concerns about this model. So adding SDCA to PDCA actually greatly clarified many of the weaknesses that are observed in the standalone PDCA model. While this approach is a standard component in TQM in Japan, it's not known in the West. And the model is roughly equivalent to the DMAIC model, but it lacks a direct correspondence on a one-to-one basis. Now, that's a problem because people then can't say, how do you go from one model to the other? And therefore, people see them as competing activities. And in reality, that's probably not need to be the case. So we see then out came the Lean Six Sigma model. So Six Sigma's model, or basic thinking model, came out of Michael Harry's doctoral dissertation, where he talked about decision filters. And he didn't use exactly the same words, but basically he had 4 filters: measure, analyze, improve, control, or what they became standardized when the Motorola Six Sigma Institute first published a discussion about the methodology of Six Sigma. Define was not in there. And he says there's 2 phases. There's characterization, which is basically what Dr. Duran called the diagnosis phase. And then there's improve and control, which they called optimization in Motorola. And Dr. Duran called that remediation, or getting better. And this revolved around this process until 1997, when Define was added, because General Electric wanted to have more management connectivity to choice of projects. But that didn't necessarily go all the way to the executive level. So DMAIC evolved across the decade of 1980 to 1990 at multiple different companies. And it was actually moving as different people saw it becoming popular, and consultants saw it a way as making money and training, that they came out and started creating their own versions. And they then reinvented it to meet their own needs for being training and their own competencies for acting as a trainer. Well, here's some concerns we had about this model. So first of all, the DMAIC is not a link to the outcome of the strategic planning process for strategy formulation or creation of improvement projects that deliver long-term change. Now, I know that this is people will disagree with me on this, but the problem is most of these come out of the within factory, not at the corporate level saying this is how we're driving the company. And so they're not strategic in the sense they're operational and making change as a project to the operational level of that daily management system. We also see that it's not tightly coupled by integration and standardization to the daily management system. Yes, we come out with control, and yes, we do figure out what needs to be trained and so forth, but not all of the DMAIC models actually involved workers and returning this to standard work conditions and formulating actually the transfer to the process owner for execution. We also see that measures for improvement may not be applied to monitor routine activities. For instance, the Six Sigma measure, it's a bunch of garbage. Why? Because if you take a look at it, it changes with the feelings of customers or the interpretation of customers or how you count opportunities or do you understand all the defects. And we see there's a wide variety of DMAIC models that's been propagated. And so we start seeing that how do you actually understand the applications of tools to those levels? And so we saw this as somewhat chaotic. It didn't get any better at all when ISO came out with their models for Six Sigma right after we'd started our process. So the need was recognized, and there were a group of people in TC 69 of ISO 9000 under Professor Tony Bendel who created their model of Six Sigma. And the problem with their model is it doesn't apply to the SMEs. That if you start taking a look at it, it's overly burdensome on statistical methods, and it's not about enough change management. So we start seeing, okay, well, how do we actually make this work better? If we go take a look at activity cost analysis, we see that this is basically a financial model for evaluating the improvement of cost drivers in an organization. So what are the resources? Identify the activities. What are the cost objects? What's creating cost or expenses? And then we have to define resources and the activities that drive the costs. What are the costs of the resources? Then we define the resource driver quality. And then we have to define the quantity of those resources that are applied. Then we can do the activity driver quantity, and then we can figure out what the calculated cost is. So it's all based on cost. And even though they're using process tools like process mapping, and very close to ideas like value stream mapping, but not quite value stream mapping, we see that it is different and it's coming from a financial perspective, not from the operational perspective of actually doing the work and improving the work that's being done. So it's mostly about accounting for how that work is being done and understanding how the costs are distributed into the system. So the concerns we have about this is was popularized in the late 1980s to early 1990s, but it never became embedded into financial management systems as a standard. ABC was implemented through the finance function in most organizations, but it was separate from the way that operational work was conducted. It's how accounting figured out where they needed to focus to push pressure on budgets or to push new projects that needed to be done from if you will, a managerial accounting perspective. So management consulting firms came in and they used this as a way to leverage, if you will, consulting contracts in companies, and they tried to have a second set of books created. ABC is not based on standard cost accounting, and so there were basically going to be two sets of books, one for standard cost accounting and one for activity-based cost accounting. And companies were looking at, we have to have two software systems, we have to have two sets of books. It never went anywhere because management didn't want to have that type of confusion in their personal obligation for fiduciary responsibility for managing the corporation. Another model that came into being was basically a systems engineering model. And here we see that there's four components here. So there's one, systems integration. There's the information security systems, how networks are engineered together, and also about technology's futures. And this process started beginning in the early 1970s when systems engineering was first created. So I got my first master's degree in systems engineering in 1975. It was one of the first master's courses offered in the world. And it was just building up at that period of time. Soon a professional organization, the International Council of Systems Engineers, or INCOSE, evolved into being in the 1990s, mostly at the service of the American defense industry, where systems engineering is very deeply embedded. And systems engineering is providing a design perspective to innovation of hybrid socio-technical systems. But if you take a look at this, it's mostly about the system components of this, and it's not so much about the people. It's about tools and how we integrate those tools into systems and so forth. And yes, there's an awful lot about this thinking process that's important. Actually, that's what the foundational process of Dr. Deming's system of profound knowledge was, appreciation of the system. And it was based on this evolving development in the early 1990s or late 1980s as he started thinking about profound knowledge. So the concerns we have about this model are that it collects methods and subjects to be considered in developing what Russ Ackoff called a system of systems. However, it doesn't provide a recipe for actually executing or linking any of those methods together. And there's a wide variety of models produced to implement this. So we can take a look at the waterfall model, the V-shaped model, Scrum, Agile, and so forth, but there's no single standard that's widely accepted. The model by INCOSE is applied for American defense industry, but it's not widely adopted for other applications. So we take a look at this, and standing back at arm's length, we see that in general, there are some weaknesses of all the models out there, and this is just considering a very high level. So there's lack of connectivity to organizational strategy. So the executives, if they establish a strategic direction, it's hard for them to launch any of these as an individual project. Second, there's a weakness in terms of linkage to the daily work standards. How do we link this strategic change to the organization to make sure the lowly work standards where value is produced in the organization, in the Gemba, how do we actually make sure that it's actually producing value in a more efficient, effective, or economical way? There's also an inflexibility relative to usable tools in the model steps. And so we don't see that there is this ability to really understand how do we do this in our business, with our process? How do these tools apply in a very flexible way so we can think clearly about what needs to be done? We also see that there's a very inefficient integration of lean, statistical process, and facilitation tools across the model. Poor standardization of generic models as they are practiced by the practitioners of those methodologies. The people who practice them do their own thing. The consultants who teach it do their own thing. And we start seeing that we've actually created a fractal organization around continual improvement models. And we also see that the lessons learned have not been approved across development of the model's design history. So what do? We had to do something. So what did we do? When we established this committee in the International Academy for Quality, we established some rules as we realized we were going to have to develop this generic model. So first rule, the front end of the model must link to the strategic formulation process of the management team. If management feels that it needs to consolidate its resources to accomplish some big, if you will, mega project that is going to be changing the organization, it should use the capability of that organization, and particularly the human resources that have been trained in systems analysis using DMAIC or whatever set of tools are out there. The second is that the back end, the result of that outcome, must be directly deliverable to the daily management system and ensure that monitoring of the measurement or changes in the measurements and the work instructions is accomplished in a positive way, and that there is a handoff from this one systemic change project into the daily Kaizen activities of continual improvement. Third, the model must be flexible enough to permit within-step change to respond to different types of data and flexible lines of questioning. So not all processes will follow exactly the same questions. Not all processes will have the same, if you will, inquiry process that require the same tools. So there can't be a fixed set of tools. We have to be flexible about it. I remember when we first started doing a Lean Six Sigma training, there was a whole group of people who said every Six Sigma project had to have a DOE. And we find today that that's not the case. What we do find is that DOE is very helpful for technical problems, but maybe some of them are going to be solved with some lean solutions. Some of them will be solved with a system solution. Some need to be solved by management decision about policy change. Some need to be actually tested to see how do people work in a human condition. And some need perhaps benchmarking to find a better solution out there. So there are many different ways that you can drive the improve phase in the process in addition to the standard idea of experimental design. The fourth is the model must integrate lessons learned from all the prior legacy systems. Seek what the masters sought, no matter what the discipline. How does it come together? And then we also realize that there's going to be a political battle. And many of you who are listening to this will probably have a political reaction to this. So the political battle is that everybody wants to see their process be a winner. And so one of the rules, and the final rule we put in place was, no process should be seen as the winner in the end. That they should all be seen as contributory to a system of change. And so we decided that when we chose the model, we would choose 7 words, because it was a 7-step model, that were different from all of the other models before. And so the descriptors would actually be not from prior models, but they would be unique. And perhaps this was the most difficult part. So the second part of this presentation is to describe this IAQ continual improvement process. And IAQ is documenting this process in a paper, which is going to be published on its website, that goes into the very detailed level, 3 steps down on how these processes actually work. So the model goes, again, roughly plan, do, check, act, which we realize is really a generic thinking approach to any scientific method. And then the 7 steps are characterize, investigate, explore, solve, evaluate, implement, and monitor. And what this is this continual improvement process is a thinking process to pull observations, what we see, what we notice in the workplace, into data to understand their relationships and thereby demonstrate causality or relationships to improve the way people work. Not all relationships are causal. And so we have to understand what is that system of thinking. So I'm going to review these 7 steps. So characterize is roughly equivalent to recognize and define when we have an enriched, if you will, DMAIC process. And recognize is the linkage to strategic planning, but it's not generally accepted in all DMAIC systems. And so this is describing the issue, the scope, and opportunity to improve. So the activities involved here are situational awareness and sense making. And that comes from social psychology and the work of Carl Wieck. It's also got strategic search, issue analysis, project formulation, which are components of a Hoshin-Conry process. So the methods included are strategic assessment, Hoshin-Conry, exploratory data analysis to figure out where we need to focus, strategy formulation, team management where we identify the improvement team, and allocation of resources and decision rights. Who's going to do what? And then the second phase is investigate. Once we've got the team, we need to understanding what is the project that they're going to work on. So they will then evaluate facts to find what are the boundary constraints that limit the pursuit of this investigation. Their activities include graphical analysis to understand flows, to understand what is engaged in the process. So failure and risk analysis is another component of graphical analysis. Understanding the value stream, where there is waste. So external risk and failure, historical investigation. And so here we see some methods like benchmarking or excellence assessment being used to understand what are those opportunities for improvement within this issue that we're trying to attack. The third phase is to explore. And here what we want to do is identify and understand the essential nature of the opportunity to improve. So here we see many of the activities that are at the second or third tier level in Six Sigma, as well as TQM. So stratification of the data, efficiency analysis, model design, process analysis, baseline analysis, and problem statements. The methods are mind mapping. So we're looking at using this because it's much more flexible to use in an IT-rich environment. Hypothesis trees, so not the testing, but understanding what is the structure of hypotheses that need to be investigated. Data integrity analysis, how good is the information? And lean process analysis, how good is the flow? We come into the fourth step, it's solve. And here what we're trying to do is to determine alternative to improve the outcome results. And so we see some activities here. This can be benchmarking, decision workouts, maybe a Kaizen blitz, a demonstration test, or a process laboratory. And so we see then we have some statistical methods here like time series analysis, which we weren't actually teaching in Six Sigma. Statistical design of experiments, ANOVA, a regression modeling. And so we can start seeing here we're going to try to understand what is this case. The next is the second half of improve. And here we're trying to do in Six Sigma is, in the continual improvement process is evaluate. And this is the second half of what many of the DMAIC improve steps have. So demonstrate the efficacy of the proposed solution. So first we develop the solution and then we determine, does it really work? So the activities can be process optimization, specification setting, what are the control limits going to be, what will the requirement limits, developing control plans, and then financial analysis to understand the benefits. And so methods include now simulation analysis, rapid prototyping, alpha beta testing, that's a verification and validation test. Verification testing is the technical testing. Validation testing is testing in the user environment of that solution to see what's the impact on the actual person who will be operating that in the daily management system. Implementation standing is moving together or merging the ideas of control and standardize. So here we're developing plans to implement and capture the benefits. So we'll take a look at now tolerance analysis, standard work process documentation, action plans for implementation, and also process leverage. How can we take this lesson to other places in the organization? So now we're talking about policy deployment, or what's called Hoshin Tenkai, like the X matrix. That's not Hoshin Kanri, but it's the deployment of the plans. Lean process control, implementation plans, and maybe what Motorola called a 4-up chart or a radar diagram, which is used in JUICE, or in Japanese TQM, to identify the various vectors upon which improvement is happening. And then the last step is monitor. So this is basically saying, how do we monitor the process to ensure sustainable results? And the idea is just like a ratchet wrench. So a ratchet wrench is moving something forward, and we have pressure one way, then it eases the pressure off, and then we move it again with pressure. And so ratcheting means we're holding the torque that we built, and we keep increasing it every time, but never decreasing it. So that means we assure a sustainable tension or torque on the system, and that way we tighten the bolt. So the activities here are the combination of SDCA and PDCA in the daily management system. We see the 3 S's, Siri, Sitan, Sisu, as part of daily management housekeeping, performance reporting, Kaizen improvements happening. And as you execute Sisu on different levels of performance, we start seeing that that is actually what Shitsuke is. And that means we are moving this into a higher level, if you will, of attention to cleanliness and discipline in the daily work. So SISU is the Muda detector of that daily management system. And when we get done with that, the end of the state, Shitsuke, is about motivating employees, training employees, getting those new work instructions distributed so people understand what needs to be done. And that system, what's called 5S, the last two steps are actually part of, if you will, a Kaizen process. So step 4 is about continuing cycles of improvement. Step 5 is basically about Kaizen, keeping to do it more and more. And the reason there are two different words we have this, that the 5S came out of plant maintenance, and then the idea of Kaizen was generated and populated through the quality movement back in the early 1950s. So we see that there's some methods used here. One is self-regulated work control, giving people ownership for the processes that they have. In Japanese, this is called Kotai Kanketsu, but it's self-regulated management. You take the responsibility for what you do. It includes improvement suggestions, so when you have ideas, you have a place to put them. And checklists and other tools of standard work so you know and can communicate what is the expectation for performance. The third part of this presentation is about quality methods that require revision or reinvention. Many of the methods we have were actually done as graphical methods for attribute data. And as we start taking a look at this digital age we're coming into, we see that we can get real-time observations of physical properties of processes, many different types of sensors, and have them all come in a constant stream. So it's not just one measure at a time that we measure, like we find in a control chart, but we're actually looking at 4 or 5 different measures of the same part of the process. And that means we now have multivariate decision-making in continuous variables. So we might be monitoring temperature, pressure, concentrations, flow rates, all at one place. So how do we put that together? It's not just by an individual control chart. So having 5 different control charts doesn't help us understand the consolidated picture of the interactions among those different factors. So we have to think differently. For more complex processes, what do we need to think about for the future? We know what we do with the simple processes, that's been well established, but how do we handle them? So there's a number of issues that we had about some of the Six Sigma methods and tools. And we're going to come back and talk about each of these briefly, but there are many more concerns we had. So the first one was the Six Sigma metric, then waste and loss analysis, including cost of quality, hypothesis testing, fishbone diagram, Pareto charts, failure mode effect analysis, statistical control charting, and you say, wait a minute, that's everything I knew. That's what I've always been doing. So yes, we have to rethink them. Do not do what the masters did, seek what the masters sought. Why did they create those tools? What was the application? What was the benefit they were going to get out of applying them? That's the question. And so all analysis methods should be reevaluated for applications in this digital environment. Now, if we're not operating in the digital environment, we don't necessarily have to do these things. Maybe we don't have to revert to this change at all. And so we have to evaluate, how do I make this work in my organization? But for those organizations that do have this need, we have to think more clearly about how will we make this happen in the future. Now, if we take a look at Six Sigma metric, so the analytic objective was that this metric was created to describe exponential performance improvements. So it was set in the early or mid-1990s, and we see that it was set because Bob Galvin said, I have to have 10x times 10x improvement in 5 years. That was the goal that was set. And when they realized this, goal was set in comparison to the stretch objective that their competitor, John Young at Hewlett-Packard, had set with his 10x objective improvement in terms of defect reduction over a decade. And so they were halfway through that process. That started in 1980, was to end in 1990 for HP. So in 1985, Motorola wanted to catch up, but they were 5 years behind. And in that 5 years, they said, well, if we move much faster and we have better effort, we should be able to do this. So this was set as an aspirational target. Okay, that's important to remember, aspirational target. And so it wasn't based on any theoretical physics. It wasn't based on what was possible. It was just based on, this is what I want to do. And that then created the Six Sigma metric because they realized that this is now an exponential function. So in comparison, the HP metric is equal to 22% compound improvement a year. Tough, but it's actually achievable. But doing it year after year means you have to keep your nose to the grindstone. You have to keep that process of continual improvement. And by the time you've done it over 10 years, you've built it into your culture. So a problem with this metric is it's a pseudo indicator. It has no direct relationship to process factors. It's also an inappropriate application of statistics. Many of the statisticians hated it. They felt like you've created your own distribution with this 1.5 sigma shift that magically appeared out of nowhere, and Michael Harry had justifications for it, but none of those were solid. And as a result of this, what happened is it was not helpful as a benchmark. Not every process has shift and drift of 1.5 sigma. I've seen them as many as 16 sigma. And so what we have to do is, if we're going to worry about the fluctuation of a process, we need to measure it, not make it a 1.5 sigma factor and guess at it. We want to have a scientific approach. So we see there is an opportunity to improve. I wrote about this in a column in the year 2000. And I said, we can actually use process capability indicators, CP, CPK, as a substitute for this Six Sigma metric. And we actually now know what it means. Because CP, CPK is based on variation observed in the real world compared to a specification that's been agreed with the customer. Those are two things that we know, customer requirements and process performance. And it's not just based on some estimation about defect per million opportunities where we don't even know what the opportunities are and we can't count all the defects. That's incomplete knowledge. We also see that there's a need to take a look at waste, loss, and cost analysis. So the analytic objective is determining potential and actual benefits from improvement, and it requires getting a clearer understanding of the magnitude of things gone wrong. Now, laudable, essential, absolutely necessary. However, the concern is this. The Toyota has 7 categories of waste that were created in the early 1950s. They were created in a workforce where people were working basically on mechanical products, cars, that had very little electrical technology to them. It was mostly in the spark plugs and generators and stuff, very classic engineering stuff. And cost of quality doesn't factor into standard cost accounting. That's another issue. And loss estimates are restricted to internal losses, not the external losses of customers, suppliers, or society. And so we see a very limited approach in every way. We don't have waste categories, if you will, that are appropriate to every organization. And so just rephrasing them doesn't matter. You say, I have to fix my waste and put it into the 7, or 8 if you have the expanded version of Toyota's waste. No. Why don't you create your own labels? Create your own operational definitions of what to mean. Create your own examples so they can become alive to your workforce. And that's the most important thing. And we can apply the idea of activity-based costing to transaction costs to help improve this objective. What is costing us something in the process? What's the difference between the fixed cost and the variable cost? Fixed cost we can't do anything about in the process. We can the variable cost. So how do we improve variable cost in the process? What do we do about managing that and reducing that type of waste? Another thing we see is hypothesis testing. I remember one of the first times I saw the Six Sigma methodology come out in the version 1 of Michael Harry's training book materials, which is called The Vision of Six Sigma. There was a hypothesis tree created by the black belts at Allied Signal. And it was very complex, and people were training to understand how do these hypotheses tests work, how do they all come together. And the analytic objective is there a statistically significant difference between samples of a variable of interest? And that could either be in the location or in the stability. So location is the mean, stability is the variation. Now the problem is hypothesis tests are single factor tests for mean difference or equality of variance. They are not useful for multi-factor analysis, and therefore they provide a limited set of analytic indicators. If we're living in this multivariate world, we can't use them. We can use something like ANOVA for comparison across multiple processes, but it also suffers from the same thing. And so it's only using one variable to take a look at different rational subgroups, where we might see like different production lines, different people, different products. And so we start seeing that we have to understand, how do we do multi-factor distribution analysis? How do we have additional indicators to explain the variations we see in a process? The fishbone diagram. I have a lot of respect for Karu Ishikawa, and he created this diagram again in the late 1970s in his book Introduction to Quality Control. We see a variety of different applications of the fishbone diagram. All of this were basically on what he was trying to do, and that was stratification. So he was using this much like he'd use a form of a tree diagram to stratify the different components of a process, so it can be broken into smaller elements and each of them understood in terms of their details. So the objective is to segment rational subgroups in a process, problem, or deliverable into its component parts so we can understand them. The problem is the interrelationship among the bones is not made visible. So if I have a bone over here for material and I have another one for measurement, how do the two interact? Well, we don't see that. And they're not made visible, and the system uses basically nominal categories instead of statistical data. What we have is labels, it's attributes. And so we don't really see what's the strength of association between those elements in the bones. Now, we start seeing that in mind mapping and the advanced mind mapping tools, we can achieve the same objective of stratification and relationship building. However, the software can also, in the advanced tools, link to the data files and allow us to do some multi-factor statistical analysis or build those linkages that say, here are those areas where we do have this potential for confounding or multivariate analysis. The Pareto diagram was created by Dr. Duran. And again, it was meant to give us an understanding to how do we separate the many different things we see from the vital few, but it's based on frequency of occurrence. And the concern we have about the Pareto diagram is that the diagram implies that the causal system includes independent variables. In other words, each of the potential observations we have of a defect category is independent of the others. And so when we have the 80-20 rule, what we say is that 80% of the defects are actually coming from just 20% of the defect categories. So those are the occurrences, okay? And that frequency of occurrence is the necessary and sufficient indicator to determine the impact significance, but it just isn't. If I have all of my problems basically a missing screw, and I only have one in terms of motherboard shortening and an electrical product, the motherboard shortening is probably much more important to take a look at, but only occurred once. And it also has a bigger cost implication. And it also has a bigger implication in terms of warranty. And so we have to really understand multiple comparisons can be made to process factors. Frequency of occurrence is one, but cost impact of events. Explanation of the total variation. How much does this failure mechanism contribute to R squared adjusted? If these are merged with Bayesian analysis, then we get a richer understanding of failure mechanisms. And that's really what we need to have. Next, we see failure mode effect analysis. So the analytic objective here is to provide a consensus view of the potential failure mechanisms and relative risk. So the concern is that classical FMEA uses something called risk priority number. And this distorts the assessment of risk by creating a pseudo scale. So there's little meaning in detection. Okay? Detection should not be used in determining risk because it's actually part of the corrective action. So it should be used in terms of risk control. And so what I really need to understand is, what is the severity of the risk? What is the probability of occurrence? And this is what they do in reliability analysis called criticality analysis. And if I don't have solid data behind this, what we start to see is this is basically a paper-based CYA approach. And look that up on Google and you'll find out what CYA means. And so what we see is that we need to have something that is more scientific. It's not driven to data, because most of the FMEAs I've seen are basically opinion-based. And opinions are not data. Anecdotes are not data. Data is data. It means that we have observed something, we've tested something, we have a physics of failure solution, we have a chemistry of failure solution, we have a human anatomy of failure solution, and we understand how those work together and compounded effects. So we do have some opportunities here. So first is, we should just use severity and probability of occurrence, and we should not multiply them together because it's a meaningless number. what we should do is present them as a polar coordinate, severity, comma, probability. And then we see directly what is actually happening for this particular thing. It's this severe and it's this probable to occur. We confound them together and I don't really understand what that means. So we can use this as a way to define risk and explain the matrix of risk magnitudes much more clearly. And finally, we come to our old favorite, statistical control charting. Now, statistical control charts were created, if you will, to identify where is variation coming from special causes that we can assign, or some activities that we can assign as a special cause in the systems. That was the assignable variation of Shewhart, and Deming called that a special cause. And that's separate from common cause. So common cause is unassignable variation. In other words, it's happening in the system. We can't figure out where it's coming from. So unassignable variation is basically included in the design of the system. It's part of what happened. We designed it to work that way. So when all the special causes are gone, those are the things that we had thought about. But the things that are left, common cause variation, that's the natural result of the process as designed. So the concern we see here are several. First of all, X bar R and X bar S charts require too much data to improve out-of-control indicators, and that delays the action for improvement. That's why Shigeo Shingo said in 1988, do not use control charts to manage the daily work process, because we can't wait to get 25 observations of 5 samples each to figure out what's going wrong with this process. And so now, at that point in time, individuals control charts or IMR charts were not being used. They didn't actually come into use, if you will, until the early 1990s. And so Deming never saw their use widely, and certainly Shingo didn't either. So their judgments, if you will, about control charting were all based on sampling distribution theory. And when you sample, what you're doing is you're adding together and you're limiting the extremes. So what we do when we sample is, if I take an individual control chart that has very high variation and I take the averages, it's dampened out. It's no longer actually seeing all of those extremes because we've averaged them out of the process. So we get an unusual visual understanding of the control chart when we look at them. So if you plot an IMR chart or just the individual's chart compared to an X bar R or an X bar S chart, what you start seeing is that the variation gets less and less as you go from the individuals to the X bar R to the X bar S chart. So how do we interpret then on the individual's chart, what are the rules for special cause variation? Those were all identified based on the assumption of a normal distribution in the data because it was sampled data. And the reason it was sampled data was we had the means of means, they're normally distributed, central limit theorem. So if I'm taking always samples and I'm always plotting the means, then those means will itself be normally distributed. However, if I have individual data, that's not the case. The case is that it will have the underlying distribution of whatever that data is. So if it's time series data, for instance, it will never be normal because we try to manipulate time series data and we try to drive it down to 0 time. If it's productivity data, it will never be normal because we try to maximize productivity and we try to drive it upwards. So we will have long tail distributions on both of those. So how do we interpret those tests? You know, what can be done when signal to noise ratio is actually indicating the causal change? And this is what we see, well, the reason perhaps that Taguchi was identifying signal to noise ratio as one of the indicators in his Taguchi experiments as a way to analyze data. So we see we have some opportunities. One is applying individual charts to enable real-time charting of variation and identify where are their excursions. But that's only valid for tests 1 and 2 of the 8 Western Electric tests for special cause of variation. And we have to think, what other tests can be used? And this is where we start taking a look at advanced applications like machine learning, or we start taking a look at artificial intelligence, where we can deal with pattern recognition and so forth, and identification of those patterns that are repeating at different time intervals. And we can then understand the lagging between times much better when we have that data systems. So here's the call to action. Everyone in the quality community who sees this is where I want my career to be, we need to assess the current state of our career. What do we think about the future? What do we know? Are we anchored in the past, or are we flexible enough to move forward? And we have to understand, what direction will we choose to embrace for furthering our career? Do we want to get stuck in the old age, and then we have a big vulnerability to, are we able to actually move forward with our career in the future? Or do we want to change? And if we've decided to change, then we have to identify what aspects are required from my personal development to be able to be a valuable contributor in the future development where quality is going. And then finally, as we take a look at this, how do we advance the profession of quality? What are the things we need to do? This is what the International Academy for Quality is trying to do now. We're trying to study all of these different dimensions, and how can we actually make recommendations to the global quality community about the things we need to think about, the things we need to do that will advance quality for humanity. Thank you very much for your attention, and I hope you have had some food for thought, and I'm sure that I'll hear quite a bit from all of you about ideas that need to be improved for the future. So thank you very much.